Alright, so for this example, we were able to take the first derivative, got negative 3x squared plus 6x. Second derivative, negative 6x plus 6. We set it equal to 0. We found x equal to 1. This is a point of inflection. Right, it's basically the cousin of the critical value. So now, step 2 is we're going to do a sign test. That's usually how I feel by now. We're going to do a sign test on f double prime based on, alright, I got a 1 there, and so I have 1 point of inflection, and so I need test values. So my test values be 0 and 2. So what I'm going to do is say, alright, now that we've done all that, f double prime at 0 is going to be equal to negative 6 times 0 plus 6, which is 6, which means it's positive. And this tells me that f prime is increasing, and it also tells me that it's concave up. So from negative infinity to 1, so from negative infinity to 1, f prime is increasing, and it's concave up. So that's the interval we found out. Now from 1 to infinity, let's see what happens. So f prime at 2 is equal to negative 6 times 2 plus 6, which is negative 12 plus 6, which is negative 6, which is negative. This tells me that since it's negative, f prime is decreasing, it's concave down, and the interval is going to be 1 to infinity. This is the point of inflection. This is where concavity changes. No, it's not an extrema. So now we're able to tell what the graph is doing. Now, honestly, we didn't do a whole lot of other stuff, so we don't know where the original graph is increasing or decreasing. We didn't do any analysis on the first derivative, so we don't know anything about increasing, decreasing, maximums, or minimums. But let me show you what the graph looks like, and let's see if we actually got it right. What was the point of inflection? What was the value? 1. So at x equals 1, which is right here, that was the point of inflection. To the left of the point of inflection, did we find out it was concave up or down? It was concave up. Is it concave up? Absolutely. To the right of it, we found it was concave down. Is it concave down?
Yes.
Absolutely. So, did it work?
Yes.
Absolutely it worked.
Yes, sir, it did.
So, I'm not going to tell you about the second derivative test yet. I'll tell you about the second derivative test tomorrow. But for today, it's all about concavity and figuring out where a function is concave. I don't want to do too much at once. And a second derivative test isn't an earth-shattering type of thing. It relates back to the first derivative test, and it has more to do with the minimums and maximums. It doesn't have anything to do with concavity. So I wanted to keep it separate from this. I didn't want to throw that in there. But the idea behind this, that if you think of different layers, and the first layer is F, the second layer is F prime, and the third layer is F double prime. The only thing we can really tell about F right here is if we do an analysis over different values, we can figure out increasing and decreasing and minimums and maximums by plugging in the numbers and all that. But here, we get our critical values when F prime of x equals 0. We can figure out increasing where F is increasing, decreasing, and we can figure out where we have extrema. So that's basically like in your first layer. We don't really do a ton. Up here we can figure out things like zeros. And up here we can figure out things like asymptotes. Whether it's a removable or non-removable asymptote. Up here we can figure out also things like domain and range. We're going to use the first derivative to find a critical value. We're going to use it to find where the function's increasing and decreasing. And we're going to use it to find extrema, relative minimums, relative maximums. F double prime, we're going to find points of inflection. Where F double prime is equal to 0.